Hello and welcome to this video on rotational motion. Specifically, today we're going to talk about the two types of kinetic energy that we typically see in an AP level course and how are they related. We've talked about kinetic energy in two different scenarios at this point. We've talked about translational kinetic energy, which has the equation 1/2 mv squared, and we've talked about rotational kinetic energy, which has the analogous equation of 1/2 I omega squared, where I is your moment of inertia and omega is your angular velocity. There are other forms of kinetic energy, vibrational, such we have here. Gamma or X-rays are a form of kinetic energy, carrying waves. Electrical kinetic energy is the movement of electrons. But these, in addition to having relatively small amounts of impact and values in terms of joules, also don't typically change much in the macro motion of objects. In other words, when you throw a baseball, these values don't change very much. So when we talk about total kinetic energy, at least for the purposes of this class, what we're referring to is the sum of their translational kinetic energy and their rotational kinetic energy, aka the kinetic energy they have from moving in a notable direction and the kinetic energy they have from rotating. The two of these combined will make the total kinetic energy, which means whenever we talk about the mechanical energy of a system, we also have to factor the rotational kinetic energy now, in addition to its other terms. So how does this work? How do we calculate this going forward? Well, it's fairly simple. If we know the mass and the radius of an object, and we know its angular velocity and its translational velocity, we can calculate its total kinetic energy. In this case, I have a solid disk rotating. I've provided the moment of inertia for you to go through and calculate the total kinetic energy of the system. Go ahead, give it a try, check back when you're done. Okay, so the total kinetic energy is equal to its translational kinetic energy, 1/2 mv squared, plus its rotational kinetic energy, 1/2 I omega squared. In this case, we're just looking for the total kinetic energy of this object, this solid disk that is rotating. So all I did was just plug in my numbers. The mass is 1.2 kilograms, its translational velocity is 5 meters per second. I plugged in its moment of inertia, the 1/2 mr squared, coming from its formula for its moment of inertia, times 3 rads per second. When I do all my calculations, I get 15.432 joules, 15 from the translational kinetic energy and 0.432 from the rotational kinetic energy. And this is fairly representative. Most objects that we deal with on a standard scale have far more translational than rotational kinetic energy, but it is enough to make an impact, especially when we start getting into larger objects. The difference and the necessity to split between translational and rotational kinetic energy also explains why whenever we talked about problems previously, we talked about boxes or carts or solid objects that don't rotate, that slide. Because if we talk about a rotating object, such as a ball going down a ramp, we have to talk about its rotational kinetic energy. If you'll remember when we talked about a tennis ball going down the ramp, we had some deviations, and we asked about why that might be. And a lot of people said friction, or it bounces slightly when it goes down the ramp, but additionally, when it goes down the ramp, it starts rolling. In short, because the object starts rolling, some of that energy is in rotational kinetic energy, some of that is translational kinetic energy, and the difference between the two is why we had some discrepancies. Not all the reasons, but some of them. So in this case, here we have a sphere, a ball, with a radius of 0.3 meters and mass of 0.7 kilograms, a fairly large basketball-sized object, maybe a little bigger, rolling down the hill. We're going to treat it as a solid sphere, and we want to find the total kinetic energy at the bottom of the hill. And solving this isn't that hard. E initial equals E final. This is nothing different than what we've done before. The problem is that my initial energy is gravitational potential energy, what the AP exam defines as U, but I will typically call EG, equals EK. The difference here is that our EK is split up into EK rotational and EK translational. And herein lies the problem, because while we have EG, this is going to be MGH. Rotational is going to be 1/2 I omega squared, and the translational is going to be 1/2 mv squared. And if I want to know how fast this is going at the bottom, I have two unknowns. I have two things I can't solve for. The I term, we can plug in the moment of inertia, we can plug in the 2/5 mr squared. We have all those variables there. But the omega does not solve. So we have omega and v, and there are two variables, so we can't solve it as it is, unless we cheat. If we remember back to rolling motion, the velocity at which this is rotating is its translational velocity. And we know that Vt equals omega r. And using this fact here, this relation between the translational velocity of an object and its rotational velocity will allow us to solve this problem. So what I want you to do is, given the setup we have here, this oversized basketball rolling down a ramp, predict how fast it's going translationally. It's Vt at the bottom of the ramp using this relation and go through. To use the proper AP terminology, derive an equation. Go through, give this a try, check back when you're done. Okay, starting from the top, E initial equals E final, so my EK translational plus my EK rotational equal my EG that I had originally. So I substitute MGH in, I substitute 1/2 MV squared in, I substitute 1/2 I omega squared in. When I substitute in the 2/5 mr squared for the sphere, I notice that each term has the mass in it, so I can divide out the mass. That'll make my math a little easier. I also then substitute in for omega Vt over r. I could have done this the other way and plugged in for omega here, and it would get the same answer. I just have to take a step back after. By solving for Vt here, I make my life easier in the long run. Since I said derive, I have to rearrange and solve this equation. The 1/2 Vt squared plus the 1/5 Vt squared, after the r's cancel here. In order to make that algebra easier, I just multiply everything by 10 to get rid of the fractions, combine, rearrange, and solve, giving me a total of 10 GH over 7. So in this case, much like we had previously, the mass doesn't matter, but the shape of it does, because that is where we get this 2/5 here. It becomes a 1/5 when we multiply by a half. So the moment of inertia is very relevant, primarily for the fraction out front. If a different object were rolling down this hill, we'd have a different value. When I plug in all my numbers, I get the Vt is 3.13 meters per second, which is slightly lower than what we had previously, or would have previously calculated, say, for a box sledding down this hill, without slipping, without friction. Anyways, thanks for watching. Have a good one.